talk about power series and using them to get high value derivatives. So what I mean by that title is the type of question you see here on the page. So we have a function equals a given power series representation, and we're asked for a high value derivative evaluated at the center. All right, so I have three examples like this in this video, kind of different types, but they're all that standard question setup. So we have a function equals a power series, high value derivative. In each of them, the number that's in the derivative here should always match the center of the original power series. So here we have a center of 3, so 3 is in the derivative. And the next one, the center here is 0, so it's 0 in the derivative. And that's the same for the last one here. The center is 0 because it's x minus 0. So 0 is the number in here. That's how these should always be set up. And they all have kind of the same strategy for answering the question. So what we'll do is set the Taylor series term with that derivative in it equal to the actual term of the given power series with the same exponent. Okay, so I need to explain what I mean by those directions, but this is going to be the key to answering all three of these. Okay, so we are connecting kind of the end result of like finding a power series representation for a function with one of the options for actually executing that, which is the Taylor series formula. So the nth derivative at the center over n factorial x minus center to the n. That's your Taylor series term. Okay, so in this first problem, my left-hand side would be the Taylor series terms, like the one term from the sigma notation, that would have the 20th derivative in it. So I said, oh, okay, well, that's just like the term with all the 20s. So we have the 20th derivative, the 20th factorial, and then the 20th exponent. 20th derivative at the center over the 20th factorial x minus center to the 20. So in the Taylor series approach to this power series centered at 3, this is what that term would be. So we want to set it equal to the actual term in the end result power series that it turned into. And the best way to make sure that it's equal to exactly the correct term is what I've written here with the same exponent. So what I mean is the x minus 3 to the 20 is the giveaway. That's the part that doesn't get simplified or changed. So we can look at this and say, well, if I want x minus 3 to the 20, that's the n equals 20 term. But in the next problem here, we have a 2n, so it's not actually the same number. So we say, all right, how do I get x minus 3 to the 20? That'll be the n equals 20 term of this power series. So I'll have 1 over n, which is 1 over 20, x minus 3 to the 20. Okay, so now that I have the theoretical term equal to the actual thing it's simplified into, I can drop the indicator. So the x minus 3 to the 20 can just go away. I needed those just to make sure I was comparing the right stuff, but since it's on both sides, it can get divided away. That leaves me with the 20th derivative of f at 3 over 20 factorial equals just 1 over 20. And solving for the 20th derivative is just one algebra step. Just multiply this 20 factorial over. And that's our answer. In this particular one, 1 over 20 times 20 factorial simplifies. So I'm going to go one extra step here and say 19 factorial, because that would be 20 factorial with the 20 divided away. So then this is like a formula for that high number derivative. All right, let's try it again with this next problem. Same setup, but a slightly trickier power series. All right, so for this power series, like we said before, because it's just x to a whatever, the center is 0. And that's why there's a 0 right here plugged into the derivative. And we're going to start off the same way by saying, all right, what term in the Taylor series formula would have the 30th derivative? It's the one with 30, 30, 30. So it'll be 30th derivative over the 30th factorial, x to the 30. That's my theoretical Taylor series formula term. And I want to set it equal to the term of this actual power series that it would like turn into. So that's the one that also has x to the 30 in it, because that wouldn't simplify. So we need to figure out, when does 2n in this case turn into 30? That would give us the n equals 15 term of this representation of the power series. Okay, so if n is 15, I have 16 over 15 factorial. That's the n plus 1 over n factorial. And then x to the 2n would be x to the 30. So again, because they both have x to the 30, I know they must be the same term. So I'm like, okay, that's this turned into this. So now I don't need the x to the 30s anymore because they're both there. This leaves me with 30th derivative at the center over 30 factorial equals 16 over 15 factorial. And again, we just have one single step of algebra to multiply 30 factorial over. So our 30th derivative is 16 over 15 factorial times 30 factorial. And those are really large numbers, so we'll leave this as a formula for the answer. All right, this is our third and final example for the video. Again, we have just a different power series for a different function. This one is also centered at 0 because we have x just on its own here, which explains why it's a 0 in the derivative in the question. So again, we want to set the theoretical Taylor series term with the 21 in it equal to the term here that actually has x to the 21. So my Taylor series term is just your standard, oops, that should be a 21 factorial, x to the 21. And then what it actually turned into was this series term that has 21. So this exponent needs to become a 21. So I just want to backtrack. How does 2n plus 1 give me 21? That would be 2n equals 20. It's the n equals 10 term. All right, so I'm going to use the n equals 10 term from this power series. That gives me 10 over 11 x to the 21. And now I say, okay, since they both have x to the 21, I can tell I'm comparing the correct two terms, and I can now drop x to the 21 from both sides. So I have 21st derivative over 21 factorial equals 10 over 11. And then again, just one simple step of algebra, bringing the 21 factorial over for the final answer. So we have 10 over 11 times 21 factorial, which again, I'll leave as a formula for the final answer since it's a really big number.